And now for the next part of our discussion on angular motion, let's have angular dynamics. You may have noted that the equations in angular kinematics follow the same form as those in linear kinematics. In linear kinematics, we have x, v, and a. In angular kinematics, we have theta, omega, and alpha. Just take the linear motion kinematics equations and replace the variables with their rotational counterparts. Replace x with theta, replace v with omega, and replace a with alpha, and you get the equations for angular kinematics. The same holds for angular dynamics. So far, in the previous videos, we have covered the concepts of moment of inertia, I, and torque, tau. I is the rotational or angular counterpart of m. Tau is the angular counterpart of F. Just replace force F with torque tau, replace mass m with moment of inertia I, and you are on your way to getting the equations for angular dynamics. So for instance, second law of motion. For constant mass, second law of motion tells us that F net is equal to ma. For angular motion, replace m by I, so moment of inertia is constant. For constant moment of inertia I, second law of motion tells us, first, F net replace with torque net, m replace with I, and a replace with alpha, their angular counterparts. And you get the second law of motion for angular motion. And it tells us that for constant I, net torque is equal to I alpha. Now, in our discussion of torque in the previous video, net torque is the summation of all the torque applied on the object. Net torque is also equal to I alpha. Second law of motion. Next up, we have work and power. Work is integral of F dotted with dx. Power P is rate of delivery of work or rate of performance of work. P is equal to dW over dt. And getting the average of this equation, we have average power, which is just equal to total work done divided by total time. W divided by T. For angular motion, work is still work, so we still have capital W for our variable, but this time, F is replaced with torque, tau, and X is replaced by theta, and we have the work done for angular motion. W is equal to integral of torque dotted with the theta. And of course, power is still rate of delivery or performance of work, dW over dt, and average power is still equal to total work done divided by time. But this time, the work done, instead of being integral of F dotted with dx, the work done is for work done for angular motion, integral of torque dotted with d theta. And for constant force, F is equal to constant. The work done is just F dotted with X. And average power is equal to total work done over total time. So W over T. Average power is also equal to F dotted with V. For angular motion, F replaced with tau with torque. So torque is constant. So for constant torque, total work done by the torque tau is just equal to replace F by torque and X by theta. We have work done is equal to torque dotted with theta. And average power is still equal to total work done divided by time. So W over T, and average power is also equal to F. Replace F with torque, V with omega. Average power is also equal to torque dotted with omega with angular velocity. Next, we have conservation of energy. For conservation of energy, mainly we are talking about mechanical energy because we are still in the topic basically of motion. Motion in a straight line, angular motion. So energy associated with motion, you have mechanical energy, you have kinetic energy, and gravitational potential energy. So potential energy basically. For kinetic energy, you have 1/2 mv squared. Gravitational potential energy is mgh. And conservation of energy tells us that initial energy is equal to final energy. So initial mechanical energy is equal to final mechanical energy. KE initial plus GPE initial plus work done by external forces is equal to kinetic energy final plus GPE final. For angular motion, kinetic energy, linear motion, we have rotational kinetic energy for angular motion. 1/2, replace M by I, and replace V by omega. Again, their angular motion counterparts. Rotational kinetic energy is equal to 1/2 I omega squared. Now, gravitational potential energy is energy associated with position. As long as that object is in a particular position, it has this amount of potential energy. So it doesn't matter whether the object is moving in a straight line or moving in a circle or rotating, meaning angular motion. Gravitational potential energy is still mgh. Now, instead of kinetic energy, you have rotational kinetic energy plus gravitational potential energy plus work done by external forces now becomes work done by external torque. So you have integral of torque dotted with d theta. You have initial mechanical energy. And then for final mechanical energy, you have from kinetic energy, we have rotational kinetic energy, and gravitational potential energy is still gravitational potential energy. So, initial mechanical energy is equal to final mechanical energy, conservation of energy principle for angular motion. Now, if there is both linear motion and angular motion in the system, that means the system both has kinetic energy and rotational kinetic energy. For instance, you have a toy top that is spinning about its axis, and as the toy top is spinning about its axis, it is moving forward. So, the system both has angular motion, the toy top spinning about its axis, and linear motion, the toy top moving forward. It has both linear kinetic energy or simply kinetic energy, and it has rotational kinetic energy. The conservation of energy equation in this case will have both the kinetic energy and the rotational kinetic energy. There's no problem combining the two or mixing the two kinetic energy equations in the same equation. It's because energy is energy. It doesn't matter if you have kinetic energy for linear motion and rotational kinetic energy for angular motion in the same equation. They both have the same unit, joules. And you will recall one statement of conservation of energy principle. Energy may be converted from one form to another. So that means kinetic energy, linear motion, may be converted into kinetic energy, angular motion. So it's okay to have the two in the same equation. So the conservation of energy equation now becomes kinetic energy initial plus rotational kinetic energy initial plus gravitational potential energy initial plus work done by external forces plus work done by external torque is equal to final kinetic energy plus final rotational kinetic energy plus final gravitational potential energy. Lastly, we have conservation of angular momentum. Momentum is P is equal to mv, and change in momentum impulse is equal to integral of f net dt. Conservation of momentum for isolated system, initial momentum is equal to final momentum. And if there is the presence of an external influence affecting the momentum of the system, rather, you have to include the impulse due to that external influence. So, initial momentum plus impulse due to the external force is equal to final momentum. For angular motion, we have capital L, the angular momentum of the object. The unit is kilogram meter squared per second. Note that this unit is different from the unit of linear momentum. Linear momentum unit is just kilogram meter per second, whereas angular momentum, the unit is kilogram meter squared per second. So we replace P by L, we have angular momentum for angular motion. So P, replace it with L, then M replace with I, and V replace with omega. We have angular momentum equation. L is equal to I omega. Then impulse, replace P by L, F net by torque net, T is still T, time is still time. It doesn't matter whether you have linear motion or angular motion. And you have the equation for impulse. Delta L is equal to integral of net torque times dt. Conservation of momentum, replace P by L. So you have L initial and L final. Conservation of angular momentum, L initial is equal to L final. And if there is the existence of an external torque or influence affecting the angular momentum of the system, you have L initial plus impulse due to the external torque. So integral of torque external times dt is equal to L final. So once again, just take the equations for linear motion, replace the variables with their angular counterparts, and you get the equations for angular motion. This applies not only with kinematics, but also with dynamics, as we have just shown. So that's it for now. In the next video, we'll continue our discussion on angular motion. In the next video, we'll talk about the second condition of equilibrium. You will recall that in our discussion of linear motion, we had the first condition of equilibrium. This time, we will have the second condition of equilibrium. So once again, that's it for now. Thank you for watching.